Okay, thank you, Duncan. So go ahead to the next slide. So just to give you an idea here, I do want to give you a little high-level overview of both OpenACC and OpenMP, very, very high level. And then I've developed 2 case studies that I hope to illustrate some of the similarities and some of the differences between the 2 specifications. And then finally, Guido is going to come up and talk some results that he's showing with SpecExcel. And then we're going to kind of both come together on some final conclusions. To the next slide, please. An important note here is that is not our intention to say one of these specifications is better than the other. They both have advantages and disadvantages. There's differences, there's similarities, and really we're only intending to highlight certain aspects of that rather than taking a critical eye towards either. Next slide, please. Another important note is that at this point in time, we had hoped to be able to run with a compiler that supports both on common hardware and give a real, true apples-to-apples comparison, and that just didn't materialize in time. So as a result, we've had to do some human compilation. Human compilation can be a little bit error-prone. We did the best we could to form what we believe a compiler would do in these situations, but of course, when we get actual compilers, your mileage may vary a little bit, so keep that in mind. Next slide, please. So to give you an idea of, next slide, please. You can go one more, please. OpenACC and OpenMP. OpenACC is currently in version 2.0. Michael just talked about version 2.5 and 3.0. They'll be coming in the near future. It is a specification for very high-level language for compiler directives, specifically designed around parallelism for accelerators, so massively parallel processors. It has an abstract accelerator model where we've found the common features of each, what we view an accelerator would look like, and we've abstracted that away. So you can represent all of this at a high level, the parallelism in your code, and not focus on the nitty-gritty of each individual accelerator. As a result, performance portability is a significant concern to us. We really want to ensure that if you take a code and develop it on one platform, that it should run well on other platforms. One of the talks earlier showed where you can further tune for the performance on a particular accelerator and make your code inherently less portable. But our goal is that things should run well for you if you develop on an NVIDIA platform or AMD platform or Intel platform across the boards. We specifically avoid adding features that would reduce performance portability. Next slide, please. For OpenMP is currently in version 4.0, and version 4.1 will be coming out hopefully by the end of this year. This is an organization that's been around since the late 90s and was originally designed around shared memory parallel processing and using compiler directives to do that. In the case of both of these specifications, in a historical sense, there were several companies that were doing competing things, similar things, and came together to try to find one unified way to do that rather than the users having to develop with one set of directives for one platform and a completely different set of directives for another. OpenMP 4.0 came out in 2013, and it really broadened that focus. And one of the biggest new features was support for what we call target devices or target accelerators. So this is for an offloading type model. We can take your code that's running on, say, a CPU, offload to another device, a GPU, or some other parallel device, and return back. So it really expanded the focus beyond shared memory parallel computers. The specific feature that enables that is the target construct. Next slide, please. So I have 2 case studies. The first one is a DAXB, double precision A times X plus Y. It's a very simple case to show on a slide. It's simple for people to understand. Of course, you probably would not write one for yourself, but it does illustrate some points. Next slide, please. So what this slide will show is a simple OpenACC version. And you can see all I've done is I have my loop across all elements in X and Y, and I accelerate that with an ACC parallel loop. Now, I have the serial reference performance on there. The performance is not really important there, but only to show that we did run it that way. The next slide will show a more fair comparison. And you can see Actually, go back. Thank you. You can see that we get a nice speed up. Now, the thing to note here, it's a parallel loop construct in OpenACC informs the compiler here is parallelism. These loop iterations are independent of each other. Now, the compiler can decide what to do with that. The compiler can decide on a GPU it makes sense to chunk it up into a bunch of thread blocks and then to use SIMD parallelization within those thread blocks. On another platform, it might choose to make different decisions. But the point is, the knowledge is there that parallel loop says, here is the parallelism, and I'm making certain guarantees to you about this loop. And just so happens, just for point of comparison here, that on the PGI compiler, it will default to 256 threads, and then will spawn enough thread blocks to fill out the rest of the loop. Next slide, please. So here is an OpenMP parallel loop. This is how most people who are familiar with OpenMP probably will recognize that I'm taking a loop and I'm going to run it across my threads. But they might not understand exactly what is happening. What happens with an OpenMP parallel? A parallel will spawn a team of threads. As soon as you spawn a parallel, that number will be fixed, and usually for most people, it's some small number, 8 or 16, or somehow mapped to the CPU cores. And then that loop is distributed across those threads. Now, the most common schedule for doing this is a static schedule. So what I mean by schedule is determining how to divide up those iterations. And so the common schedule would be statically decide that. So right up front, give each thread one over n threads worth of work. And it's usually the contiguous iterations, because that makes a lot of sense on a CPU where you would want to make sure that you're iterating across your cache lines and you're able to do a SIMD sort of vectorization. So on the next slide here, you can go and advance it. What I've had to do is, because I didn't have a compiler that could do this, I had to write my own kernel of how this would be implemented on a GPU. So a lot of people believe if I have a parallel do, I should be able to just turn that into a target parallel do. So a target parallel do says offload the data and the execution to the target device, spawn a team of threads there, and then use the same work sharing rules that I explained on the previous slide. Now, there are certain aspects of work sharing, including the ability to have critical regions, the ability to have barriers, the storage of thread local data. That means that on a GPU device, really, if you're going to strictly interpret the specification, this means this must be done in a single thread block, because that's the level of synchronization that's available on our GPU devices. And so what we have here is, if I assume the same static schedule that I just explained, you can see and I've, for academic honesty, put the kernel that I wrote up here. Again, a compiler might choose to do things a little bit differently, but you can see the performance is actually quite poor. And there's two different reasons for that. One, well, we're only running on one thread block, so we're really throwing away a lot of performance that's available to us on the GPU. GPUs love to have lots and lots of thread blocks so we can hide the certain latencies, so we can spread across all the streaming multiprocessors, so that actually we get fairly poor performance. But there's a second subtlety that you may not realize, and that is that the static schedule that we've defined actually results in really poor memory performance on a GPU. So by giving each thread a contiguous set of loop iterations, what that means is that thread 0 and thread 1 will be accessing it in strides throughout memory. So on a GPU, we like to have consecutive threads access consecutive or nearby elements in memory, and then we coalesce them down into as few memory transactions as possible. In this case, it will result in something that's perfectly uncoalesced, which means really poor memory bandwidth. But there's a pretty easy fix to this, and I'll show that on the next slide, please. So in the static schedule, you can provide an optional chunk size. This is not something that people commonly do on CPU architectures, but we do have this option. If I give a static chunk size of 1, what that means is I'm going to perfectly interleave my iterations. So thread 0 will get iteration 0, or since I'm in Fortran here, thread 0 will get iteration 1, thread 1 will get iteration 2, and so on. And so by interleaving those, then we get what is a more natural type of memory access pattern for a GPU, which allows us to coalesce. So you see our performance improves quite a bit. But unfortunately, we are still running on one thread block, so the performance is worse than OpenACC, and we should still be able to do much better. Now, I will comment that there may have been an additional way to do this. It may have been that if we had done a parallel for SIMD, that the compiler may have the freedom to do this as well, but the interleaving gave me what I needed in order to do this. So this is something that anyone developing a compiler using OpenMP for GPUs will need to think about, the fact that the default schedule that we're used to doing on CPUs is really a poor schedule to be doing on GPUs. Now, there is an additional way to specify parallelism in OpenMP 4. And this was something that was really designed for more GPU-like architectures. If you move to the next slide, please. That is the target teams distribute parallel do. And so this is a lot more typing, but it gives us a lot more freedom. So this directive, once again, we take our execution and our data and we offload it to the GPU. But now, instead of creating one team, we create what we call a league of teams. And how many teams we create is implementation defined. So if the user doesn't specify how many teams to create, the compiler has the freedom to choose that. So on an architecture where we only need one thread team, well, okay, we get one thread team. That's fine. On an architecture like a GPU where we really want lots and lots of thread blocks in order to fill up the GPU, we have that option as well. So here we create a league of teams. We distribute our loop first across those teams, and then we use the standard work sharing within those teams. So unfortunately, I don't have a compiler to do this, but in theory, I don't see a reason why this should perform that much differently than an ACC parallel loop. There may be some subtleties that could influence that, but as a whole, my expectation is that if you were to write your code this way, it should get somewhere close to an OpenACC parallel loop. And the fact that Michael Wolf is nodding gives me a good acknowledgement to that. Next slide, please. So some takeaways on this case study. ACC parallel loop expresses the parallelism and lets the compiler decide what to do with it. It's really as simple as that. You have one way to do this. You express the parallelism, and no matter what architecture, the compiler will decide what to do. In OpenMP, there are several ways to do it. And a target parallel do, which I think is tempting for a lot of people. A lot of people think, I have parallel do's or I have parallel fors in my code. By the way, I did this in Fortran because it's really simple to do CUDA Fortran and OpenACC in the same file. But the same should be true in C as well. Target parallel do is really not sufficient for GPUs. It doesn't expose a lot of parallelism. Now, I do need to acknowledge that if everywhere in your code you do parallel do, parallel do, parallel do, or parallel for, parallel for, parallel for, the compiler might be able to figure out some of this stuff for you. It might be able to look and see, OK, we don't synchronize. We don't have a critical region. Everything is completely visible here, and I can determine for myself that this is a fully parallel, independent loop. And then if it did so, then it might choose to take some extra steps and break this up. That, in my opinion, and I think most people who have read through the spec would agree, that is not technically legal. But if you as the user still get the correct results, then you might not care that that's not legal. So some compilers are investigating doing this, and I know of several compilers that are investigating this possibility. Target teams distribute, parallel do, and I'll add in there, you might as well, if you're going to type that much, add an extra SIMD if you can, is more portable because we have the option of running on one thread block and get the exact same behavior as what we had up above, or we can have many, many thread teams and as a whole result, thread blocks. And of course, the more you as the programmer specify, the less portable it becomes. Next slide, please. Now I want to talk a little bit about differences in how asynchronous programming is done in the two specifications. Next slide, please. So I have on OpenACC, we have an async clause and a wait directive. So what I could do is I have an ACC parallel loop. I could say make this asynchronous on some handle. That handle specifies which asynchronous queue. And I can do an update on that same asynchronous queue, and then I can later wait. And so I can build up pipelining and do this. So this turns out to map really well to CUDA streams, and I don't think that's by accident. That you can have, pass in individual numbers, and those will translate to stream numbers, and it maps very well. Next slide, please. In OpenMP, well, there already was a way to do asynchronous behavior with the CPU, and that was using OpenMP tasks. So the initial thought was, let's just use OpenMP tasks. And so what you'll see is we would put a task around our target region, and we put a task around our update, and that's fine. The problem is that because these tasks are running on the CPU, that first task has to fully complete. It will launch onto the GPU, wait for that GPU to complete, then it will complete the task before it can then start the next one. So all of this CPU interaction has to occur. And what that means is we're not able to queue up a bunch of work in the CUDA stream, and so there's going to be these bubbles that occur in your timeline. Now, okay, this is a trivial case here where really I probably could have put both in the same task, but we can extend this out to more complicated cases. So as much as possible, if in this case you really would want to fuse these tasks together and to make this work. But we acknowledged the fact that in OpenMP4 this is really not well designed for architectures like NVIDIA has, and we would like a way to be able to take advantage of hardware queues, such as CUDA streams or OpenCL work queues. So in OpenMP 4.1, next slide, please, we've expanded the capabilities a little bit. So now the target region is going to be a task. And so what you can do is you can place your task dependencies on your target region. And you can also mark these as no wait. So we borrowed a term that was already in the specification and say, no wait, and what happens is this target team's distribute will get put onto the device, into the device's work queue, with a certain dependency here. And so return control immediately to the CPU, which is going to come down here to this update and do the same thing, put it into the CUDA queue or the OpenCL work queue, no wait, it'll return back to the CPU, and the CPU can keep going until we hit this task wait. This really, I think, is a nice approach. If you will notice with the dependencies that OpenMP provides, I think it really does provide a fairly rich dependency graph that you can build out, and you still get that richness with this. But you also have the ability to take advantage of hardware queues, to immediately put this into a CUDA stream and come back without the need for the CPU to check things off. Now, it would be a valid implementation for the compiler to still do this with CPU tasks, but now they don't have to. Now they have the option to use CUDA streams, for instance. And so we think this will make things quite a bit better at 4.1. So next slide, please. So in case it was not completely clear why this is an improvement, on top here we have a 4.1 implementation where I have a CPU task that launches a target directive, and the target directive executes on the GPU and then eventually returns to the CPU, informs the CPU that I'm done, and it can then issue the next task. So you'll notice these gaps in the timeline as it occurs, whereas in the 4.1, the intention is that it will be possible to enqueue all of those on the GPU and then wait on all of this to occur. So we believe this will be an improvement. Next slide, please. So takeaways from this, Guido, you're just about up. Async and wait were not accidentally designed to map really well to CUDA streams and to OpenCL work queues. OpenMP 4.0, we had good intentions to reuse what we already had. However, while they're really expressive, they do require CPU interaction, which we think is a little bit crippling on a GPU architecture. And so we've improved that with 4.1, which is coming later this year. You can read about this in the tech report that was released last year. It provides the richness of task dependencies, and you can interact with CPU tasks and GPU tasks can synchronize with each other, and it removes the requirement for the CPU to get involved. And I do want to point out that both of these models are compatible with OpenMP tasks. So if you have an OpenMP task in your code, you can mix a target region with your existing CPU tasks, or you can place OpenACC and OpenMP tasks as well and fully mix your dependency graphs. So we think that this is a nice solution. So with that, I think next slide, we're moving on to Guido's portion.
Thanks a lot. Did I turn this off? No. OK. So thanks a lot for the handover. Now, from someone who actually defines the specifications to someone who has to use them. Since I'm working with Spec and the SpecHPG group, we spent the last 2.5, 3 years working on an accelerator benchmark so that you can benchmark not only MPI and OpenMP, but also the offloading paradigms. And so what I'm trying to present here, or what I will present, are some apples to oranges comparison that we did using this benchmark suite. I'm not saying that we did all this right. So I don't know how many hours Jeff and I already spent discussing subtleties of the standards and things that we did that we could have done better and so on. But I'm trying to give kind of a user's perspective here. And actually, I'm going to show some performance numbers from some platforms that we have available. Next slide, please. So what SpecExcel is a set of comparative performance metrics. You use one device. So it's a benchmark that does offloading to one device. You measure the capabilities of the accelerator plus the surrounding software platform. And basically, the overall box. Everything has some certain contribution to it. If you're having a certain very theoretically capable hardware accelerator, but a crappy software environment, this will hurt your performance, and you'll see it within those applications. What's part of the benchmark are computationally intensive parallel HPC-oriented applications from ranging just a couple lines of code to many thousand lines of code to kind of give a broad spectrum of what HPC users would implement and build and use and see how this works. It's important that the applications should be as portable as possible. So that's why at the moment there is an OpenACC 1.0 suite and an OpenCL suite, because those are there are at least multiple compilers and multiple hardware platforms you can run on. That's why there at the moment is not an OpenMP 4.0 suite. So what I'm going to talk about first is the OpenACC suite. Thanks. Next slide. It contains a whole bunch of applications in C and Fortran. Some of them are actually originating from the OpenCL suite that have been ported over to OpenACC. Some of them are individual codes. Some of them are codes that were previously in the Spec OpenMP suite that have been the OpenMP CPU suite. So let's call it the OpenMP 3.0 suite that have been ported over to OpenACC, so where the directives have been exchanged. And some of them are basically ports of well-known other benchmarks where they've been ported to OpenACC. Next slide. And the hardware that we used was Tesla K40, Intel Xeon Phi early access platform. So it's not a Phi that you can go out and buy. If you want to go out and buy a similar platform, the closest you can get is a 2010P, I think it's called. An AMD Radeon R9 290X. And the host platform is basically a dual sockets Intel Xeon processor system. But the processor doesn't really matter that much for the benchmarks. And if so, since we are all plugging all those accelerators in the same host platform, you always take the same performance hit on them. Next slide. So now doing OpenACC runs using the PGI compiler that can actually target both, so an AMD and an NVIDIA GPU. What you're seeing here is those are runtimes. So there's I'm kind of taking my spec hat off because then I would have to show rates. So I'm just looking at pure runtimes, being the pure researcher at the moment. And so lower is better. And you see that there are some benchmarks where the AMD is better than the NVIDIA, and some other it's vice versa. This is a good thing for you as a user, because you can go look at this and say my problem is similar to that code that's in there. So a good choice for hardware for me might be one of those platforms, or you could be that you're an NVIDIA developer and saying, why is my hardware doing so bad on this? It shouldn't be the case. There are like 2 outliers there. If you could advance just one more. This one right here is, I believe, fixed in the new, upcoming PGI version. So this was basically something PGI internal. And next one. There is actually where you're hitting, or we were hitting a memory limit of the AMD card, and you had to do some kind of reshuffling and offloading. So basically splitting kernels into multiple kernels to multiple data regions to cope with a limited amount of memory that the AMD GPU had, and that costs you extra cycles. So this is not a an unmodified version of the benchmark. Actually, we had to do some code tweaking to get it to run on the AMD GPU. Next. And now for the fun part. I had an extremely bright student who had just said, for the fun of it, all those marketing guys tell us, this is OpenACC, OpenMP. What's the deal? They're trying to do the same thing. It's similar. They're all doing directives. How hard could it possibly be to port this, benchmark suite? It's just a couple of applications to another, way to describe parallelism. Well, it turns out it's a little more difficult than you think, because as you look at it, it's about 4,000 directives and 6,000 lines of code. And next slide. As we've already heard, new with OpenMP, you get those target directives with the idea, you got this new device that you can offload things to. The host can also be a target. So, that's kind of universal. So putting this in isn't really hurting you if you're not actually having a target. Then you have those directives to control the data transfer. So all this kind of sounds similar to OpenACC. Next. And then you start porting, or should I call it translating, or then you notice, some of those translate pretty directly. There's this ACC Parallel that's kind of like your target teams, and then you have your ACC loop that you can have. That's the distribute, and then some of them, then you run into those fine subtleties where things on paper look as they should be working, and then also we had to say we were working with this Intel Xeon Phi platform, and the Intel compiler that was still in the process of implementing the OpenMP 4.0 spec. So some of the things that, some of the hoops that we had to jump through, we are not even clear if we are not understanding the standard, or if Intel didn't understand the standard and just implemented things weird, or if it's just a broken runtime or a broken compiler or a bad platform. So to get those codes to run with the right selection of directives was an interesting experience, and was a fun 2 months for my student. And I don't know how many tickets to Intel, support tickets. All right, next. Let's talk about some of the ones that don't really translate well. There is somebody within OpenACC came up with this ACC Kernels construct, which I don't know how that came about, but this is like the poor man's -- auto parallel. You just put it in there and, go out, compiler. You're smarter than I am. Try to find something to do. Unfortunately, OpenMP doesn't have an equivalent to this. The ACC loop is, depending if you're actually giving some scheduling information with it, it maps to different things with OpenMP that actually do different things and actually have a dramatically different performance on the device. So if you want to, build something that supposedly works, you want to pay close attention. This OMP parallel work share idea that it's in OpenMP, there's no equivalent directly in OpenACC, so you might want to use this, but you have no idea with those OpenACC applications, where you might map that to. And then, as I said before, some of those OpenACC applications in the suite have already been ported at least once or twice. So now you're porting them for the second or third time. It also introduces some fun parts because you're starting to see effects of this poor application being, ported back and forth, where some errors you're seeing, it's just not clear, where they're coming from. Then synchronization. If you do an ACC parallel, there is no barrier between loops. If you have loops in between, if you do an ACC kernel, there is a barrier between those two. Scalars. OpenACC can handle scalars extremely well. OpenMP 4.0 targets do extremely bad with it. There are just things that don't work. Next. Giving you some examples. Now let's look at code. You see this PragmaACC kernels, and somebody was nice enough to put some ACC loops in there to hint to the kernel or to the compiler what you want to do and how you want to distribute it. So you have some worker and vector scheduling help. And you can now go ahead and translate this. Say, you want a Pragma OMP target region, offload the stuff to the target, and then do an OpenMP Parallel for. You have to do a private for the temp so that it does the right things. And you can use a Pragma OMP SIMD to kind of do the similar thing that the vector means, but it's not exactly the same. So it's the closest you can get. And we could have a great language discussion if that's really correct what I'm doing here. So far, Michael is not, beat red and starting to throw things at me, so I'm still okay, I guess. Next. Then there's this ACC Parallel, and you have those two loops in here. Basically, what I want to say is, with ACC Parallel, if you do this, those two loops could potentially run concurrently. If you want to have the same effect with OpenMP, you have to add this no wait clause and hope that oh, he's shaking his head. Okay, well, then I'm right? Yeah. Ah. Did somebody record this? Michael Wolf said I'm right. Thank you. Okay, so, and you have to hope that this no wait is actually interpreted by the compiler, the OpenMP compiler, to do what you want it to do. Next. And then come ACC kernels. So if you find codes like this, that basically means now you have to play compiler because there is nothing in the OpenACC portion that gives you any help on what's going on. And this is where you will spend your time. So you have to introduce all of this yourself to kind of convert the PragmaACC kernels to the equivalent what PragmaACC Parallel would have been. So yeah, this is where you will spend time on. And if you have a code that has a whole bunch of those in there, I don't know who programmed that. Well, that's what it is. That's what it's going to take your time. Next. Yeah, copy and p-copy. This, well, gets solved in the upcoming OpenACC standard. But at the moment, you have to look carefully what you want to do. So if you're looking at the code to the left, you're seeing I'm doing a copy of X and a p-copy of Y. And then later on, I'm doing a kernels where I'm doing, again, a copy of X and a p-copy of Y. Now I'm not allowed to do that. But those codes are in the spec. This is code examples from the SpecExcel suite. So you have to look a few rows behind you to somebody who worked on that. And maybe he can point fingers again to somebody else who actually owned this benchmark. So in that case, you have to translate this to the correct semantics. So in the beginning, you say both are mapped. And then for the second one, for the nested data clauses, you have to pay attention to, one is updated. That's the copy, because you're kind of forcing it to update. And then you're mapping again the Y. Next, please. And again, map versus update. What does a variable actually mean once you're in nested regions, especially nested target regions that happen when you actually run a script that converts some of the one-to-one translation we actually did with a script to get them in there, and then you find some weird things going on where you have nested parallelism, and you have to make sure that the mappings so that the variables you're getting are actually mapped correctly so that you're still producing the correct results. Next. And now for one of the fun things that us as Spec has been keeping us busy for the last couple of weeks. To declare target or not to declare target. Actually turns out that both left and right, both OpenMP, are exactly valid OpenMP. And there are compilers that do the left side, or actually require the left side, and there are compilers that can also live with the right side. You notice the subtle difference. You have a global variable that you use in a function later on in a target directive. And forget the map. It doesn't belong in there. And one thing is you can declare those variables as target variables, which means that as your program is started, they are already allocated on the device and will then be transferred over, or will then be updated as you enter it. And there are some, on the right side basically means any scalar variable that you find that you know about as a compiler because it's in your lexical context, you'll do an map to from around the target region. Now, since both is valid OpenMP, and if you don't do the left side, some compilers from a famous company not far away from here that's producing chips, for example, requires it this way, then you're wondering, what do I have to do now? Do I have to do the declare target, or do I actually want the more implicit way that's also available? So difficult thing, both is valid OpenMP, and some compilers do it one way or another. I don't know what to do about this, interestingly. Next. And then the fun with loop ordering. So one of the things that we noticed is, if you have OpenACC, you do this OpenACC Parallel clause. Just say you have a loop, collapse the 3, distribute them over the threads that you have available, and magically, the compiler does the right thing, reorders loops, does the right stridings that fits well on the GPU, and boom, you get performance. With OpenMP, what basically happens is that you have to pay special attention to loop ordering. It's still true that for some reason, as soon as it's starting to enter OpenMP regions, especially the Intel compiler that we use, all of a sudden forgets about a whole bunch of code optimizing capabilities that it actually has. So reordering loops to get a better striding for the Xeon Phi doesn't work, so you have to do this manually. And then we tried different ways of actually doing this, where to do the SIMD, where to do the collapse. And the runtime difference you're actually getting is dramatically. So if you do KJI, so that's the example on the top right, runs about 6 seconds. If you do the variation on the lower right, the runtime goes down to 0.2 seconds. So, and you would actually expect the compiler to be able to do that. Come on, it's just loop reordering. It can't be that difficult. You know what the target architecture is. So why, as a programmer, do I have to care about this? So we actually had to go through a whole bunch of those nested loops and rearrange the loop orders to kind of, because we wanted to see how good can you actually get on the device. Let's put it this way. Next. And then the collapse clause by itself. For how far do you want to collapse? You have those 3 perfectly nested loops. You could say collapse 3 if you want to. It turns out, if you do just the loop without a SIMD construct and you do collapse 3, that gives you an extremely long runtime, which actually works. If this were OpenACC, this would be great performance. If you do a collapse 2 and then throw some SIMD directives in there, or not even do it SIMD directives, runtime goes down. If you do a collapse 1, and basically what the message is, although you have 3 perfectly nested loops, don't do a collapse over all of them. Just do at least 1 less, because for some reason the Xeon Phi with the Intel compiler would like to have, at least for their threads, still to have a loop. So this is not, you would express this differently with OpenACC, keeping in mind that you're actually targeting different hardware. Next, please. And now, comparing various fruit. This is probably the slide that you've been waiting for. So keeping in mind that our port or translation might not be perfect, so adding the blue bars, meaning that's the Xeon Phi runtimes, in the same rules, kind of adhering to the spec rules, but reporting runtimes lower is better. You're seeing that, for example, for 303, you're actually getting better than the AMD GPU. And the raw performances of the devices are comparable, flop-wise. So in theory, you should actually be seeing similar performances for all of them. So the differences you're seeing are basically screw-ups in the hardware implementation or screw-ups in the software stack, low-level software stack, or screw-ups in the compiler maybe. And then, so you're seeing a couple of outliers. In general, you see that the Xeon Phi is, taking a slightly higher runtime than everybody else. We've talked to some of the Intel developers about this. Not very helpful. We talked to some other folks who did try those, apples and oranges comparison. It turns out that if you turn profiling on this Xeon Phi, you're seeing a whole bunch of cache coherency traffic, basically eating up your memory bandwidth on the device. So somebody at Intel decided that it's great to have a cache coherent accelerator, but didn't really pay attention to how cache protocols actually work. And if you do a Snoop-based cache protocol on 60-something cores, boy, that's going to eat memory bandwidth. And this is what you see right here. This is one of the impacts. And that's basically why you're typically, if you talk to other folks, you typically see if you're going to a Xeon Phi, you see probably a factor 2 performance drop comparing it to an NVIDIA GPU. And this is basically because half the time, you're doing the cache snoop first before you're actually doing the memory transaction. So every memory transaction actually turns into 2. Even though all the other hardware is kind of similar from theoretical points of view. Next. And just because we have some energy measurement attached to the whole system, we also try to see what's the average power consumption during those runs. And interestingly, you see different kind of profiles right there. There are some benchmarks where the power consumption is a little less, while on the others, most interestingly on the Xeon Phi, it kind of, you turn it on and then all of a sudden, you kind of have equal power consumption. For the NVIDIA and the AMD GPU, this actually goes up and down. Really depending on how busy you keep the device. And keeping the device busy can be two things. Either the device is shoveling memory around on its global memory to its registers, or it's actually computing. The low power numbers that you're seeing here is when the host device interface or communication is actually eating up a lot of time and nobody is actually doing anything, the CPU not and the GPU not, or the accelerator not. And you're only stressing PCI Express. Next. That would be your cue, Jeff.
So I guess to wrap things up here, some things that we wanted to stress here is that OpenACC and OpenMP both provide features that are aimed at accelerators, but the two are not equivalent. There are strengths and weaknesses to each. And differences, some of which we are actively working to resolve within both committees. Work parallelizing to one is in some ways transferable to other, but how much work and how much effort is involved, as Guido has shown, will vary according to the codes. And hopefully soon we'll be able to do more apples-to-apples comparisons using real compilers. But today, which hardware you choose may dictate which directives you wish to use. So with that, we're open up for questions.